Hi guys, hope all are good. So, last video we have seen the Gauss law. Now we are going to see the application of Gauss law. Application of Gauss law. See, the Gauss law is easy, but applying the Gauss law is a bit tricky. How we apply the Gauss law? Just now I will tell you. Let us suppose I have a hemisphere like this. Hemisphere means half a sphere. Okay. So now let us suppose we keep a charge here. Q charge is here. So obviously the field will be there generated by this charge Q, and flux will be leaking out of this surface. But as you know, this is not a complete 3D closed surface. So to make it 3D closed surface, what we will do here? So we will make complete 3D surface, right? Now you can see it is a full-fledged one sphere. We know that the flux leaking out of this surface should be equal to Q by epsilon. By which law? It is a Gauss law, right? So now what we will do, as we know that this is a full geometry, so half flux will be leaking out of the surface and half leaking out of this surface. So we know that this, let us suppose this is phi 1, this is phi 2. So phi will be equal to phi 1 plus phi 2, right? As you know that this is a symmetrical, or we can say these are both similar geometries. So we can say that phi 1 equal to phi 2, right? So now the phi equal to phi 1 plus phi 2, that is equal to 2 phi 1, right? What is phi here? Q by epsilon, right? And it is 2 phi 1. So phi 1 is equal to Q by 2 epsilon. So we can say that the flux leaking out of this surface, this particular upper surface, is how much? Q by 2 epsilon, right? Now let's move to the another question. So we have to find out the flux leaking out of the cylindrical surface, right? Okay, so let us suppose this is a cylindrical surface and we just keep a Q charge here at the center of the cylinder and at the top surface, right? If the length is L, radius is R. If you want to find out the flux, how we will find the flux? We know that here it's not a full 3D geometry, it is 3D geometry, but charge is not kept at the center. So what we will do here? We will do one full cylinder. Now we can say that the flux leaking out of this is Q by epsilon, but as it is a half surface, so flux leaking out of this surface will be Q by 2 epsilon, right? Yes. Now one more question is, let us suppose we kept a charge at the edge of the cube here, which is kept here. So how we will find now? We know that this is not complete geometry. So what we have to do? We have to make one more cube here, one more cube here, one more cube here. So this is how we have to cover it whole. If you think, then you will find that we have to make the 8 cubes to make it at center, right? How many cubes? 8 center. 2 will be, so if I make a top view here, so we will see this, the charge is kept here, okay? So 2 is down. If we make one more 2 here, then it will be totally 8. So now, so the flux leaking out of this this particular cube will be, we know that the flux leaking out of the total 8 cubes, right? So how much flux will be leaking out of the single cube? That will be flux is equal to Q by 8 epsilon, right? So it means total flux is leaked by 8. So what is the contribution of this cube? It will be 8 Q by 8 epsilon, right? Okay. So now we will see So flux leaking out of the phi by a disk. Okay, so now how we do that? Let's take a small disk here. Okay, some charge q is kept here. Okay, we'll do what we'll do here now. Let's suppose this is the disk. We want to find out the flux leaking out of this surface, right? So what we'll do, we'll make a small element here, small element or elemental ring here, right? Let us suppose this here. So this thickness, take it out, this small ring, right? This is the charge q here. So the thickness is d. Okay, the radius is r, thickness is dr. So the area vector will be like this, and the field will be like this, E. This is dA and this is theta. Okay, so now if I find out the flux leaking out this small ring, this is elemental ring, this will be d phi equal to E vector dot d, right? So it will be how much now? E dot dA cos theta. This theta, okay? If you observe carefully, this theta angle is nothing but the theta angle made by the center. Let us suppose this is the distance, let us say x, this is L distance, right? So what is cos theta here? Cos theta is x by L, right? From this we can see that this is theta, this is theta. So if it is x, it is L. So we can say this is x by L, right? So now d phi. So d phi is equal to E dA cos theta, right? So phi equal to integration E dA cos theta, right? Yes or no? You see here, this field is also not constant here, right? If it is a sphere like this, then we can say the field at every point is constant at every point. But it is a disk. Actually, this is a charge. Charge is kept here. And this is a disk. So field lines are not, actually they are not similar. But if it is a sphere, then line will be similar. But here lines are not similar. So the field will not be similar, because we know that field is nothing but, field is what? K Q by R square. So if this distance changes, so obviously field also changes. That's why the field throughout this disk is not constant. It is what? Disk, right? So field throughout this disk is not constant. So what we will do now? So let's find E. E is what? K upon KQ by this is, let's say, L. So KQ by L square, right? What is dA? dA is, let's open this, break this, and we'll find out small area dA is equal to, this is dr and this is how much? 2 pi r, okay? As it is the length r, sorry, this is the radius r, so it is 2 pi r into dr. dA is 2 pi r dr, okay, right? So let's find out the phi is equal to E in place of E, K Q by L square, and dA is 2 pi r dr. And what is cos theta here? If you see carefully, what is cos theta here? It is x by L. So what? X by L. So it is x by L, right? Okay. So now K will come out, KQ, 2 pi will come out. We have x is also come out, because we know that x is constant here, right? X is the distance here. Okay, x is also comes out. So k cube out, 2 pi r, 2 pi out, x out. So we will have a the 1 upon L square, right, to R dr, right. Now, so there are two variables, L and R. L and R. So how we will do that? Let's see. So what is L value here? See, what is the L value here? L value is nothing but it is, if you take this triangle, see this triangle. This is L, right? This is X, this is R, right? So we can say L is nothing but under root R square plus X square, right? Into, sorry, this is R d. Okay, as it is square. So now we know that k q 2 pi x into R dr and R square plus X square, right? R square plus X square. So how we will solve it? We don't know, because here R is variable and X is not variable. But let's change this to R square plus X square equal to T square. Okay. So we have to convert it because we cannot integrate it, right? So limits are from R equal to 0 to capital R, right? Because we can make extreme element here and we can make extreme element here also. So this is, so differentiate dt by dr. It means we have to differentiate with respect to R on both sides. We are assuming it, right? Both sides, right? So we can see 2 dt by dr is equal to 2r. Okay. So by the differentiation with respect to r on both sides, we will get this 2 will be cancelled. So we can say, okay. So now, sorry, 2 cancel. So t dt equal to r dr, right? And limits for x equal r equal to 0, for r equal to 0, x equal to t. See here, if you keep r value 0 here, you will get x equal to t here, right? If r equal to capital R, then t equal to under root x square plus r square, right? Now, so k q 2 pi x into t dt by, this is t square dt, right? I think it's q, right? I think it's q. So it is 3 by 2, right? 3 by 2. So it's tq, right? tq. Okay. So k and limits from t equal to x to t equal to under root x square plus r square, right? Now we solve it, k q 2 pi x, so it will be minus 1 upon t. So the integration of this will be t square, t will be cancelled, this is dt by t square. So limits from t equal to x to under root x square plus r square, right? Solve it, you will get, and what is k? K is nothing 1 upon 4 pi epsilon into q 2 pi x into, do it, so you will get x minus under root x square plus r square, 1 upon x minus 1 upon under root x square plus r square, right? So 2 pi will be cancelled, so you will get q by 2 pi epsilon, sorry, 2 q by 2 epsilon into If you multiply by x inside, so you'll get 1 minus 1 upon under root x square plus r square. So this is nothing but, this is cos theta. See, suppose this angle is making, so now what we will do here, so q upon 2 epsilon into 1 minus this under root 1 upon under root x square minus r square is nothing but 1 minus cos theta, because it was, and it was a disk. So if it is angle theta, charge q here, so this is the flux leaking out of this disk. So actually it is behaving like a cone. As you can see, it's a cone. So it means if I have a cone like this, and here keep a charge q here, and this angle is making theta, so we can say phi is nothing but q upon 2 epsilon into 1 minus cos theta. So thank you guys, hope you understand this. So in next video we will discuss the applications of Gauss law. By the help of the Gauss law, we will find out the field of a cylinder. There are two types of materials, non-conducting and conducting. In non-conducting, the charge is not at the surface, charge is inside the body. Okay, so in the next video we will discuss the application of the Gauss law in for the different bodies. Okay, so thank you.